All right, take a close look at this. You're looking at the microscopic world inside a computer chip. The kind of thing that powers your phone, your car, pretty much everything. But what you're seeing isn't just some fancy tech. It's actually the physical solution to a ridiculously complicated math puzzle. So, what is this puzzle exactly? Well, that's what we're going to dive into today. It's called the Max K-cut problem, and it turns out getting a handle on this thing is absolutely key to designing the future of technology. So here's our game plan. First up, we're going to look at why this puzzle even matters in the real world. Then, we'll get into the nitty-gritty of what it is and why it's so ridiculously hard to solve. From there, we'll uncover a brilliant strategy for cracking it, check out some really stunning results, and finally, we'll take a peek into what's next. All right, first things first. Let's connect this kind of abstract idea to the real world. I mean, why should you or I care about something with a weird name like MaxCut? Well, because it's everywhere. Seriously. It's fundamental for designing those semiconductor layouts we just saw. It's used to make massive computer networks run better. It even helps AI systems, see and understand the world around them. So here's the bottom line. When we get better at solving this one problem, we unlock better, faster, and more efficient tech pretty much everywhere. Okay, so we get why it's a big deal. But what actually is it? To really get the puzzle, we first have to understand the board it's played on. And that game board is what we call a graph. Don't let the name scare you. It's super simple. It's just a bunch of points, we call them vertices, connected by lines, which we call edges. Think about a social network. All your friends are the points, and the friendship between you is the line connecting you. See? Simple. Okay, now for the actual challenge. Picture this. You're planning a party, right? And you have to put everyone at, let's say, K different tables. Now, your goal isn't just to fill the seats. You want to arrange people to get the most conversations happening between the tables, not just people at the same table talking to each other. That right there is the Max K-cut problem. It's all about splitting the points into groups to get the maximum number of connections that cross from one group to another. So let's break that down into 3 simple steps. Step 1, you take your problem, say that ship layout, and you turn it into a graph. Step 2, you color all the points, which is basically just assigning them to one of your K groups. And step 3, you count up all the lines that connect points of different colors. The whole mission is to find the coloring pattern that gives you the absolute highest score. So you might be thinking, why is this so hard? I mean, if it's just coloring and counting, can't we just tell a computer to try every single combination? Well, that's where things get really interesting. The fancy technical term is APX hard. Basically, this problem is in a class that's like the Mount Everest of computer science. And what that means is, it's not just that finding the one single perfect answer is nearly impossible. It means that even finding a pretty good answer is an insane challenge. It's kind of like trying to find the highest peak in a huge mountain range, but you're blindfolded, and you have no idea if your next step is going up or down. And here's the kicker. For any graph that's even a little bit complex, the number of possible ways to color it in is, well, it's astronomical. We're talking numbers with so many zeros, you'd get tired writing them. Trying every single one to find the best, a supercomputer would be crunching away for longer than the age of the universe. So yeah, brute force is not an option. We have to be way smarter. Which of course brings us to the solution. If you can't tackle the whole giant puzzle at once, what do? You do what we've always done with big problems. You break it into smaller, more manageable pieces. This is the classic divide and conquer strategy. So the algorithm gets to work. It takes this huge, messy graph and starts to intelligently break it down into its core fundamental components. It's like it finds the natural weak points or seams in the puzzle and just splits it apart right there. Then, for each of those little pieces, it does something really clever. It creates what's called a dual graph. You can see it here as this new blue map. Now think of it this way. If the original graph shows all the connections, the dual graph maps out the spaces in between those connections. This trick lets the algorithm see the problem from a completely different angle. It highlights where all the potential conflicts are, which makes the whole thing much easier to figure out. And then, using that brand new map, the algorithm can find the single most efficient way to sort out all those internal conflicts. It finds something called a minimum perfect matching, which is just a fancy way of saying it finds the absolute best way to pair up and solve all the issues with the least amount of fuss. And it just does this for every single component, one by one. So what is this magic tool that makes this whole elegant breakdown possible? Well, it's a really powerful data structure, and it's called the SPQR tree. And this slide shows you exactly what it does. And it's brilliant. On the left, you've got a complex, jumbled up mess of a graph. On the right, look at that. You see how the SQR tree has organized it into a clean, logical structure. It literally transforms chaos into a roadmap that a computer can actually follow. And the way it works is by sorting all the little pieces into 4 main types. You've got your S for simple series chains, P for parallel connections, Q for a trivial single link, and R for the rigid, more complex bits that are left over. By sorting the puzzle pieces like this, the algorithm knows exactly which tool to use for each specific part of the job. Okay, so all this cleverness, all this complexity, does it actually work? Does it pay off? Well, let's look at the numbers. Okay, wow, this is where it gets really, really impressive. Just look at this chart. Take that top line, a problem with over 83,000 nodes. Without this smart SPQR method, it took a computer almost 45 minutes to solve. But with it, look at that, just over 3 minutes. That is a 92.6% reduction in time. I mean, just let that sink in for a second. This is not some small incremental speed up. This is a fundamental, game-changing leap forward. And what that really means is that a problem that was, for all practical purposes, unsolvable at this scale suddenly becomes manageable. This is how you get those big breakthroughs. This is how you design even more powerful and more complex computer chips. So this is an absolutely incredible step forward. But, the story's never really over, is it? The challenges are always getting bigger and more complex. I mean, think about it. Our world is only getting more interconnected, more complex. The networks, the chips, the AI of tomorrow, they're going to be represented by graphs that make the ones we saw today look tiny. So the question isn't just if we can solve them, but how. Will it be with even smarter divide and conquer algorithms like the one we just saw? Or are we going to need a totally new way of thinking, maybe something powered by AI or even quantum computers, to find that next perfect cut?